Is there any cis-trans isomerism in tetrahedral structures? Is there such thing as cis-trans for tetrahedral? No, because if you look at it, they're all adjacent to each other. Do you see that? No matter which one you pick, it's going to have an adjacent species 109 degrees from it, right? And so everything's adjacent in tetrahedral, so we don't use cis-trans. Actually, we don't use mirror face in this case because I suspect you could use mirror face for this and it would work, but we call this something else, and let's talk about that something else. Is it a structural isomer? It's not a structural isomer because all the bonds are the same. It's just a different three-dimensional arrangement. And so what we conclude is this isn't really a geometric isomer as a typical geometric isomer. This is what we call a optical isomer or an enantiomer. And so let's talk about those right now. Whoa. What optical isomers are, and these fit it, is this. Optical isomers are non-superimposable mirror images. And so if you look at this box here and you draw another box next to it, which is its mirror image, if you can superimpose this second box on top of the first box, then they're identical structures. But if you can't, then they're optical isomers or enantiomers. And so here we draw this box with a blue corner here. We draw its mirror image here, and then we try to rotate this to make it match with this. And so this has a hole on the top, so I'll just rotate this 180. If I rotate this 180, the blue lines up on the wrong corner here. And no matter what I do to rotate this, I cannot get it to match. And so this would be called a non-superimposable mirror image. In other words, an optical isomer or an enantiomer. And so these are stereoisomers too. These are not structural isomers. Here. The most common stereoisomer are optical isomers or enantiomers, or your hand. You know, the right hand is a mirror image of the left hand, but when you try to rotate it to superimpose, they do not superimpose on each other. And so they're enantiomeric. In other words, we have another word, they're chiral. That is, anything that's chiral is an optical isomer. And so what you did here was you generated one structure, and then take a look. It's mirror image. We can draw. And then we'll try to rotate that mirror image to see if they're superimposable. And so if I draw the mirror image of this here, let's do it. Here. The mirror image would have A in the center here, B on the top. And then coming to this side would be C, and then going back and out of the board would be D, and going back and into the board would be E. And so it looks the same, right? But when you try to rotate it, and so let me rotate it so that BAC line up here, BAC. And so I'll take that, rotate it here to get BAC, and then this D gets flipped to the back and in position, and this E gets flipped out here. And so when I look at E and D, they don't match. And then if I try to flip this so that D and E match, then B and C are going to be screwed up. And so there's no way to rotate this so that they superimpose, so that means these are two unique structures. And so the answer is two isomers. And if you want to name them, we call these two enantiomers, or two optical isomers. say that. And so when we're looking for stereoisomers, this is what we do. First, we look for geometric isomers. Cis, trans, mer, face. For each of those structures, we test it for enantiomers. And so each structure, in order to test it for enantiomers, you build the mirror image and then see if the mirror image superimposes. If it superimposes, it's the same structure. If it doesn't superimpose, then it's an enantiomer. And so we have to test each isomer for optical isomerism or optical activity. Okay, so this is important because in biology, a lot of enzymes are optically active. And that is, there's a certain arrangement that the enzyme must attach to the substrate molecule. And so let's say an enzyme here docks the C here, the D here, and the E here. So there's a site for each of these atoms. And so the enzyme will fit this substrate molecule, but it will not fit this substrate because the D and the E's are now flipped in position. And so in nature, all the enzymes work like this. So that means that only one of these isomers is biologically active for a given enzyme. And so we can digest things like what's a glucose? Glycogen. Glucose molecules linked together. Sugar. Glucose is sugar. And glycogen has a link in one three-dimensional versus cellulose. You know what cellulose is made out of? Wood. Cellulose is made out of sugar, right? So wood is made out of sugar, except it's linked in a different three-dimensional arrangement, which means that we can digest glycogen, but we can't digest cellulose. Whereas like termites, they can digest cellulose. They wouldn't be able to digest glycogen because of this. Right, 3D. And the same thing with drugs. If you have like buy Advil, you're wasting half of it, because when they synthesize this, they get both isomers, usually 50-50 mix. Right, and so that means only one of these is biologically active, and the rest, either lead to side effects or is just wasted. Right. And so that's why the talk the other day is interesting, because she's trying to do stereoselective synthesis. That is, synthesize only one optical isomer, not the other. It's not easy to do. Well, where does the optical come from? The term optical. Optical comes from this. Let's say you have light come in. When light comes in, what does it interact with? It interacts with electrons. And it depends on where the electrons are. Let's say a certain wavelength of light will interact with the AD bond here. And so if the light's interacting with the AD bond, then the photon of light comes in and then starts to vibrate the electrons in the AD bond here, right? And so it would rotate this way. Whereas in the other isomer, the D is on the opposite side, right? And so in this isomer, the light gets rotated this way because it starts to interact with these electrons. In the other isomer, the electrons are on the opposite end, so the light's going to be twisted this way and interact with electrons and bond this way. And so the origin of optical activity comes from the rotation of polarized light. Here, one isomer rotates it alpha like this, the other would rotate it negative alpha, like that. And hence we have optical activity just because of where the electrons are, which side of the molecule they are on. If you have a 50-50 mix, then what happens is it doesn't rotate it anyway because it cancels out. Plus alpha minus alpha ends up giving us a 0 when we hit it with polarized light. And so this is an optically active sample. If it's enantiomerically pure, that is, we only have one enantiomer in there, it rotates it this way. If we put the opposite enantiomer in there, it rotates it the other way. If we put a 50-50 mix in there, no rotation. It's called a racemic mixture, but you don't have to know that. All right, so let's get some practice with the optical isomers, but some more practice with geometric isomers. In fact, we're going to practice with all isomers. And so do these two. The first one you're going to do is this, trisethylene cobalt 3. Tell me all the isomers for this and name them. This could be structural or stereoisomers. If it's stereoisomers, it could be geometric and or optical or enantiomers. And then do this one. It's going to be COCl2 En2. How would we name this?
Dichlorodiethylene cobalt 1.
Close.
No.
Very close. Almost. Okay, someone else? Or you want to try again?
Dichloro.
Oops.
Dichloro.
Bis.
Bis.
Yes. Bis, dichloro, bis, ethylene, diamine, cobalt 1 or cobalt 3. Good. And so yeah, dichloro, bis, ethylene, diamine, cobalt 3. Tell me how many isomers you generate and what they are.